And thank you all for coming. As Landon said, I'm Kieran Liebeck, and today I'll be discussing challenges and directions for designing safe and secure augmented reality systems. This is work done in collaboration with Yoshi Kono and Franzi Rosner at the University of Washington. So let me begin by asking you to suspend disbelief for a moment and imagine a world in which, by wearing nothing more than a pair of specialized glasses like those shown here, digital content could be seamlessly overlaid and integrated with your perception of the physical world. A world in which immersive, interactive content, such as a video game, could almost come to life with virtual content that looks nearly real. Or perhaps more applicable to the audience here, imagine attending a conference where you didn't have to deal with the nuisance of attempting to read name tags that so often fail to face in the right direction, but instead had a wealth of information about your peers readily available, such as name, affiliation, or authorship information. Or perhaps a particular talk caught your attention, and you want to more interactively explore the findings and results. And of course, when you need a break from a long day of talks, you could always distract yourself with a quick session of your favorite game. While these scenarios may seem like science fiction, they are in fact not as far off as you might think. We're starting to see this vision manifest in the form of augmented reality technologies, or AR for short. We define AR to be any computer-generated sensory feedback that is overlaid on a user's perception of the real world, often in real time. This feedback could take many forms, including audio, visual, or haptic. However, we'll be focusing on visual feedback throughout this talk. Indeed, we're starting to see a rapid increase in interest and investment in new emerging AR technologies. These systems are becoming more and more capable of supporting a broad range of applications, spanning a wide spectrum of domains, ranging from health to maintenance to entertainment and more. And leading these efforts are a number of organizations within the tech industry who have begun investing heavily in AR technologies, as well as a range of groups in the automotive industry who have begun exploring the ways in which AR can enhance the driving experience. In fact, due to the collective efforts of these groups and others, AR is projected to grow into a $100 billion industry by the year 2020. So the bottom line is these technologies are coming, and they're coming faster than you might think. Even now, in the early stages of these emerging AR technologies, we're starting to see their potential capabilities, from relatively simple activities, such as real-time text translation, to more immersive multi-application settings that blend virtual content into a user's view of his or her physical environment, as seen in demos of Microsoft's new HoloLens AR glasses shown on the bottom. So on the left, we have a demo debuted during the Super Bowl that overlays a 3D animate football player into your living room with some additional information. And on the right, we have a suite of AR applications, such as a tabletop weather app, a 3D robot companion, as well as a web browser and video player. And we've also started to see sophisticated driving aids like BMW's new AR glasses that sync with external cameras on a car to provide X-ray vision, allowing drivers to see through the body of their car. Or Jaguar's concept AR windshield, shown on the right, that displays virtual cones to aid new drivers in training. These efforts indeed demonstrate that sophisticated AR technologies are on the horizon. However, many challenges remain before this vision can be appropriately realized. Despite efforts to move towards visionary new AR technologies, there exists a significant gap between what is possible today and what AR could hypothetically enable. And the ways in which we bridge this gap will ultimately define how this future plays out. In the ideal case, we would end up with immersive content that integrates cleanly into our perceptions of the physical world. However, if we fail to appropriately bridge this gap, we could see a future that plays out in undesirable ways with a plethora of spurious, distracting, and possibly frightening content littering our views. But figuring out how to best bridge the gap between today's AR and the AR of tomorrow is no small task, due in part to a number of key challenges. For example, we're seeing a trend towards platforms that need to support multiple applications simultaneously augmenting a user's view with three-dimensional virtual objects that interact with some representation of the real world. These are serious technical challenges and ones that industry players are likely considering. However, they are further compounded by a multitude of both input privacy risks due to the potential of malicious or buggy applications to collect sensitive sensory information from a user's surroundings, such as video feeds or audio recordings, as well as output security risks due to the ability of apps to overlay arbitrary augmentations on a user's view of the real world. So given these risks, we argue that the time to consider malicious and buggy actors who threaten input privacy or output security risks is now, while AR technologies are young and malleable. And we note that we are not the first to identify this need. Prior efforts have begun exploring the privacy risks surrounding sensory inputs. However, no prior work to our knowledge has characterized the spectrum of visual output risks, and our work focuses on addressing these output security challenges. The ways in which existing systems handle the presentation of visual content were not designed with these new AR scenarios in mind. So we argue that there is a critical need to rethink visual output paradigms for AR if we are to bridge this gap. And to better understand the need to address the various risks involving AR output security, we can consider the spectrum of issues that might arise along several axes of application behavior. The first being who or which application can display certain content, what kinds of content apps can display, where apps can draw within the context of a user's view, and when apps can draw based on the context of a user's actions or environment. And to better flesh out these axes, we'll walk through several examples now. So first we consider who or which application can display particular content. For example, knowing such information could be useful in disambiguating content generated by honest apps from content generated by more nefarious advertising or phishing applications, such as the one shown here. Next, we consider what kind of content apps should be allowed to display. For example, while it may be permissible for an automotive AR app to overlay route guidance information on a user's view of the road, displaying a virtual pedestrian, for example, could mislead the driver into swerving or crashing, leading to physical harm. We can also consider where applications should be allowed to display content within the context of a user's environment. For example, as before, it may be permissible for an app to display information over the road, but occluding other vehicles or critical objects like road signs would be detrimental to both driver and bystander safety. And finally, we'll consider when an app is allowed to display content based on the context of a user's actions or environment. For example, while it may be acceptable to display a virtual football player while the user is watching the Super Bowl in the confines of his or her home, displaying the same figure while the user is crossing a busy street could cause distraction and again lead to physical harm. And while these examples are by no means comprehensive, they can hopefully start to illuminate the range of visual output risks that might manifest in the absence of defensive mechanisms, as well as the critical need to constrain application behaviors. So given these risks and challenges, we ask, how can we design AR platforms that support flexible new scenarios while simultaneously mitigating the risks of malicious or buggy applications? Referring back to prior works aimed at mitigating input privacy risks, we note that there is a promising body of work that proposes to augment the operating system of an AR platform with trusted modules that filter and regulate sensory inputs. Similarly, our main proposal here is to introduce a trusted output module as part of the OS. This module would allow the operating system to play an active role in regulating app behaviors by interposing on AR content before it is displayed. This would, for example, allow the OS to prevent an automotive app from occluding other vehicles, as in the example before. We also propose two broad axes along which such a module should be designed. The first being control, or how much power the OS has to constrain application outputs, and the second being flexibility, or the ability of the OS to support a diverse set of rich application behaviors. And to flesh out the design space of visual output modules at a high level, we will first consider two natural strawman approaches, followed by our proposed direction. One natural model for managing visual content is the standard windowing model employed by traditional desktop applications. So we can begin by exploring how such a model might map to an AR setting. Returning to the multi-application HoloLens demo from before, we can observe how this mapping might play out. We have some two-dimensional content that might fit naturally in some sort of windows tethered to a user's walls, as well as stationary three-dimensional content that might fit naturally in some sort of 3D windows, or windows that logically map to regions within a 3D representation of the user's world. This model provides a number of benefits, much like in desktop systems. Visual outputs from different apps are isolated from each other, and they are confined to bounded windows positioned by the user, allowing the OS to exert coarse-grained control over the placement of virtual content. However, consider a scenario in which multiple applications wish to display dynamic 3D objects that need to move throughout the user's environment. It is not clear how traditional windows would support such movement, as this would entail applications essentially moving their own windows. Furthermore, if windows from different apps were to overlap, then objects could occlude each other in undefined and possibly undesirable ways. So to recap, while windows provide a certain degree of control over visual outputs, they provide insufficient flexibility for rich AR scenarios. And what this model starts to illuminate is the inherent tension that arises between supporting flexible app behaviors and exerting control over virtual content. So given the flexibility limitations of Windows, we can see how this tension might manifest again in a design that intentionally favors flexibility, which we refer to as free drawing. Rather than constraining application outputs to isolated windows, this model treats the user's entire field of view as essentially a shared window upon which multiple apps can simultaneously display content. While such a model would support dynamic virtual content moving throughout the user's view, it would clearly allow applications excessive freedom in displaying content, such as a virtual pet application that goes a bit out of control. And so again, we can see this tension between flexibility and control manifest, and thus we ask, is there a new way of thinking about output management that eschews variations on traditional windows in favor of something more tailored to unique AR scenarios that could allow us to support reasonable levels of both control and flexibility? While there may be many possible directions for such a model, our key idea is to design an output module that manages visual content at the granularity of individual AR objects rather than the coarse granularity of windows. And by AR objects, we mean OS primitives that act as abstract representations of AR content that apps wish to place throughout the user's view of the world, and whose positions and behaviors can be managed by a trusted OS module. By elevating AR objects to first-class OS primitives, excuse me, our model allows the OS to understand more complex interactions that would be unachievable in the previously mentioned models, such as collision events between objects of different applications. This also allows the OS to maintain some representation of the user's physical world and to manage object interactions within the context of this shared world, as well as to dynamically update these objects and to support flexible behaviors for applications. Additionally, this model allows the OS to constrain visual outputs at the granularity of individual AR objects. For example, a user running several apps may wish for a virtual pet to move about his or her room, and also for football statistics to be overlaid on his or her TV while watching a game. But perhaps the user may not wish for the virtual pet to occlude the TV. In essence, the AR object model allows the OS to contextually constrain behavior at the object level while simultaneously allowing rich application behaviors, achieving both flexibility and control over virtual content. Given its capability to enforce policies at a fine granularity, we believe the AR object model is a step in the right direction for managing visual outputs. However, we don't yet know how to best exercise that capability, and a number of design challenges remain. First, we need to consider what policies or constraints might be appropriate for different scenarios. For example, reasonable policies while a user is lounging in bed may not translate well when the user is doing something potentially hazardous, like operating burners on a stove. We also need to consider how various parties, such as the user, app developers, or platform designers, should be able to specify constraints, as well as how the OS might be able to efficiently evaluate those constraints, especially if some of them are conflicting. And last but not least, it remains open what the appropriate APIs to expose to apps might be. Supporting flexible behaviors without incurring too heavy a burden on developers would be critical for such a model to operate and succeed. And so I hope that through this talk I've been able to impress upon you that while sophisticated AR technologies are on the horizon, many challenges remain before AR can reach its full potential. This includes a range of key technical challenges, along with critical input privacy and output security risks. We focused here on characterizing the risks from outputs from malicious or buggy actors, and we proposed augmenting the operating system of AR platforms with a trusted output module to manage visual content at the granularity of AR objects, allowing the OS to balance application flexibility with exerting control over outputs. And finally, while many open questions remain, and while our model is by no means the last word on this matter, it establishes a framework to engage broad consideration on the diverse issues surrounding AR outputs. Thank you for your time. Happy to take questions.